Hi, welcome to my presentation on Boyer-Moore algorithm variations. My name is Dusan Damjanovic. I am a student on the Master's Studies at School of Electrical Engineering. This presentation is a part of a project for Genome Informatics class. For this project to be made, a paper is used titled Variation on Boyer-Moore String Matching Algorithm, a comparative analysis from 2012. I will talk about Boyer-Moore string searching algorithm and its heuristics, bad character and good suffix rule, and Boyer-Moore horsepool and its improvements, Boyer-Moore horsepool Sunday and Boyer-Moore horsepool Sunday 2. Lastly, we will see the results of a performance analysis run on various tests. The Boyer-Moore is an efficient string searching algorithm that is the standard benchmark for practical string search literature. It was developed by Robert Boyer and J. Strother Moore in 1977. The algorithm pre-processed the string being searched for, which we will later refer to as the pattern, but not the string being searched on, the very text. It uses knowledge gained from character comparisons to skip future alignments that definitely will not match. The Boyer-Moore algorithm uses information gathered during these pre-processed steps to skip sections of the text, resulting in a lower constant factor than many other string search algorithms. In general, the algorithms run faster as the pattern length increases. The key features of the algorithm are to match the tail of the pattern rather than the head, and to skip along the text in jumps of multiple characters rather than searching every single character in the text. And to skip these characters more efficiently, various heuristics are proposed. For example, the bad character rule is the first heuristics we're going to talk about. It works this way. If we mismatch, we use the knowledge of the mismatched text character to skip alignments. It works this way. Upon mismatch, let B be the mismatched character in T, and T is the text. Skip alignments until B matches its opposite on P, P being the pattern, or P moves past B. The second heuristics, the good suffix rule, is markedly more complex in both concept and implementation than the bad character rule. It is the reason comparisons begin at the end of the pattern rather than the start. For example, let B be the substring of P text that matched a suffix of P pattern. Skip alignments until B matches opposite character in P, or a prefix of B matches a suffix of B, or P moves past B, whichever happens first. And if we are going to use a combination of heuristics, for example, in the tests which we will see later, we used good suffix and bad character rule together, and two different variations of Boyer-Moore horsepool improvements. And if we do things this way, after each alignment, use the algorithm that skips more. When it comes to improvements of the heuristics, the Boyer-Moore horsepool is a string matching algorithm that compares characters from the end of the pattern to its beginning. When characters do not match, searching jumps to the next matching position in the pattern. In other words, the Boyer-Moore horsepool algorithm is an algorithm for finding substrings in strings. How does Boyer-Moore horsepool algorithm work? To explain it, we will find A, B, C, D in the string that we are seeing right now on the screen. The first step is to construct a bad match table as value equals length of a substring minus index of each letter in the substring minus 1. The value of the last letter and other letters that are not in the substring will be the length of the substring. This value will be assigned to the letter in the bad match table. The next step is comparing the substring with the string. In this step, you start to compare from the index of the last character in the substring. In this case, it will be the letter D. If the letters match, you should compare the previous letter. If the letter does not match, you should check the value in the bad match table of the letter in the string that you compare and move the number of spaces that the value indicates. You should repeat this step until that all letters are matched. It's very easy to implement in case of a mismatch, and the removal of could suffix might decrease the shift. That is the downside of Boyer-Moore-Horspool. If we would like to improve the Boyer-Moore-Horspool algorithm, we might do so by adding the Boyer-Moore-Horspool Sunday. The core idea is in the calculation of bad char function. Consider the situation of the next character, namely the use of the next character to determine the right offset. If the character does not appear in the matching string, skip that step by pattern length +1. Otherwise, match strings in the far right of the characters to the end of the range +1. In the matching process, the mode string must not be asked to compare. It does not match is found. The algorithm can skip as many characters to match the next step to improve the matching efficiency. In Boyer-Moore-Horspool, the maximum shift achieved is equal to pattern length, but in Boyer-Moore-Horspool Sunday, the maximum shift that can be achieved is equal to one more than pattern length. If the last character is not in the pattern, but next to last character is in the pattern, a problem happens because less shift is achieved as compared to Boyer-Moore-Horspool. The improvement to that is Boyer-Moore-Horspool Sunday 2. The idea of the algorithm is when mismatch occurs at any position, then the right shift value is determined by next to last character, a last character of text corresponding to pattern. Now, matching starts from last character of pattern. If mismatch happens at any position, then consider next to last character of text and find its position in pattern. There are three cases. First case, if it's not in the pattern, then right shift by m+1, m being the position of the last character. Second case, if it occurs at first position, then right shift by m. That if this occurs other than the first somewhere other than the first positions, then the shift is calculated as x. And consider last character of text corresponding to pattern and calculate shifts. If shift calculated by this is x, then shift by x. Otherwise, shift by m+1. As said, m is the position of the last character. This algorithm considers last character and next last character, both, so it combines the advantages of both Boyer-Moore-Horspool and Boyer-Moore-Horspool Sunday. Searching overhead increases as we have to take care of two characters for calculation of shift. For the performance testing of the mentioned algorithms, I used three different patterns on each of the three test files. The three files, Coffea arabica, chromosome 1C, Maspachari, chromosome X, and Cynoglossus semilevis, chromosome 10. Each of the three files are provided by National Center for Biotechnology Information. The performance tests are made for cases. First, the combination of Horsepool Sunday and Horsepool Sunday 2, each of them individually, and lastly, the combination of good suffix and bad character rule. And for each of these cases, we will try finding 3 different patterns, as you can see in the table. The time performance of these cases are shown in these bar charts. What is apparent is that the Horsepool algorithms can be up to twice as fast as the good suffix and bad character heuristics. It is also apparent that the Boermore Horsepool Sunday 2 seems to be the quickest one. Here you can see the table of the previously showed results in the bar charts. Every unit is measured in seconds. For memory analysis, the Horsepool heuristics wins again by far, but it should also be noted that the combination of different algorithms also affects the memory that is shown here in the bar charts and here in a table. Every unit is displayed as a byte. So this will be my presentation. Thank you for your attention.